Today on Professor Explains, the X-ray image formation sequence. I will discuss how electricity is transformed into X-rays. Understanding this process is the foundation of radiographic physics. Step 1. Filament current. The process begins at the cathode, which contains one or two tungsten filaments inside a focusing cup. When you prepare for an exposure, a low-voltage, high-current circuit heats the selected filament to over 2,000 degrees Celsius. As the filament heats up, its outer shell electrons gain enough energy to escape. This process is called thermionic emission. These free electrons form a negatively charged cloud around the filament called the space charge. Step 2. High voltage is applied. When you press the exposure button, the generator applies a high voltage potential, measured in kilovolts peak, or kVp, to the X-ray tube electrodes, the cathode and anode. The cathode is negatively charged, while the anode is positively charged. Because opposite charges attract, the electrons are rapidly accelerated across the tube. kVp is the maximum electrical voltage applied across an X-ray tube to accelerate electrons and create X-ray photons. Depending on the selected kVp, these electrons can travel at nearly half the speed of light. The higher the kVp, the greater the electron speed and kinetic energy, resulting in more penetrating X-rays. Step 3. Electron interaction with the anode. The electrons collide with the tungsten target. This sudden deceleration converts the electron's kinetic energy into other forms of energy. Approximately 99% of the energy becomes heat, while less than 1% is converted into useful X-ray photons. That's why the anode rotates, to spread the intense heat over a larger surface and prevent damage to the target. Step 4. X-rays are produced. Two types of X-rays are produced during these interactions. Bremsstrahlung radiation, or braking radiation, occurs when high-speed electrons are slowed or deflected by the nucleus of a tungsten atom. This produces X-rays with a range of energies and accounts for most of the useful X-ray beam. Characteristic radiation occurs when an incoming electron ejects an inner shell electron from a tungsten atom. An outer shell electron fills the vacancy, releasing energy as an X-ray photon with a characteristic energy unique to tungsten. Step 5. Shaping the beam. The X-rays leave the tube through the tube window and then pass through filtration, which removes low-energy photons that would be absorbed by the patient, increasing patient dose with no improvement to image quality. Next, the beam passes through the collimator, which restricts the beam to the area of clinical interest. Proper collimation reduces patient exposure and minimizes scatter radiation, which will improve image contrast. Step 6. Image formation. The X-ray beam passes through the patient where different tissues absorb different amounts of radiation. Dense structures, such as bone, will absorb more X-rays, while soft tissues that are less dense allow more photons to pass through and reach the image detector. The remnant radiation reaches the image receptor, where it's converted into analog signals that are transmitted to the computer for processing and display. Key takeaways: remember this sequence: filament heating, thermionic emission, electron acceleration, target interaction, radiation production, filtration, collimation, patient attenuation. Then the remnant radiation reaches the image receptor. Think of the X-ray imaging chain as your roadmap. Once you understand the steps, you'll have the framework needed to understand image production, image quality, radiation interactions, and many of the physics concepts you will see on tests and on the ARRT exam. Learn the process. Instead of memorizing isolated facts, you'll understand how each concept connects, making it easier to solve exam questions and become a more confident radiologic technologist in the profession. I'm Dr. Delia Lofton, radiography educator. I hope this explanation helps you understand, not just memorize, the X-ray production process. Like this video, follow for more Professor Explains lessons, and visit the link in my bio to join Rad Imaging Academy.